Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of today's lecture is Simultaneous Heat and Mass Transfer. So, now in this lecture we will be taking a situation where both heat and mass transfer are taking place. So, then how to obtain the mass transfer flux and then heat transfer or temperature distribution, etc., those things that we are going to see. Okay. So, consider a hot vapor A is diffusing at steady state through a stagnant film of non-condensable gas B to a cold surface at y is equals to 0 where A condenses. So, hot vapor A is condensing on a cold surface, but when it reaches the cold surface, in between there is a stagnant film of non-condensable gas B, and this A is diffusing into B when it reaches to the cold surface and condenses in that process. Okay. So, then under such conditions what is the concentration profile of that component A, and then what is the temperature profile, that is what we have to find out. Assume ideal gas behavior and uniform pressure. Assume physical properties to be constant evaluated at some mean temperature and composition. Neglect radiation heat transfer, right. So, this is the simple statement of the problem. So, this problem we can divide into two parts. First part, as I mentioned, developing concentration profile Xa as function of y, temperature profile as function of y, as shown be figure in the next slide, as shown in the figure next slide, right. So, when mole fractions and temperatures at both film boundaries are known at y is equals to 0, at y is equals to delta. Thickness of non-condensable gas film is delta. It is having two boundaries, one boundary location is y is equals to 0, another boundary location is y is equals to delta. At either of at both of these locations, what we know the temperature and concentration. So, boundary conditions are known. So, this we are going to do when by taking non-condensable gas film B. So, NBZ, that is what we are taking 0 here, right. And also when both heat transfer and mass transfer are taking place, so then there would be different film thickness in general. So, delta x, delta t, but what we are assuming that it is same here, whether mass transfer or heat transfer, the film thickness is same. That is the assumption, that for those conditions we are obtaining Xa as function of y and t as function of y. The second problem what we are doing, we are generalizing the results for the situation where both A and B are condensing. Now, not only A, B is also condensing on cold surface, right. So, then that A and B are we cannot say that B is non-condensable and then its flux is 0, that we cannot say now, because it is also condensing onto the cold surface. Okay. And allowing for unequal film thickness for heat and mass transport, then we are taking delta x is not equals to delta t is not equals to delta. So, then what are the solutions, that what are the concentration profiles and then temperature profiles, that we are going to find out. So, pictorially we have a cold surface here which is designated as y is equals to 0, and then close to this one there is a boundary of stagnant gas film made up of B, right. So, now the direction of diffusion or condensable vapor is coming in this direction and then reaching this cold surface and then condensing like this here, right. Fine. The coordinate system is taken such a way that the direction in which the change in concentration or temperature is occurring, that is y. Film thickness is delta. So, at y is equals to 0, t is t naught and Xa is Xa naught. At y is equals to delta, t is t delta and then Xa is Xa delta. So, now for this case we are going to find out this 2. This is part A. To determine the desired quantities, we must solve the equations for species conservation and energy equations for this system. So, then this is the species conservation equation in generalized form, vectorial notation it is given. If you expand this one, for species A, you have this one, dou Ca by dou T plus dou by dou x of NaX plus dou by dou y of NaY plus dou by dou z of NaZ, and then reaction, there is nothing occurring, no reaction occurring, so Ra is 0, right. And then what we have seen, diffusion or the concentration variations and temperature variations are only in y direction. So, only NaY would be there and that would be function of y, whereas NaX, Naz are 0, and then it is a steady state problem. So, this is dou Ca by dou T is also 0. Then we have this one, dou by dou y of NaY is equals to 0. So, now if you know the NaY, you can find out the concentration profile, very conventional way that we have been doing. Okay. Before getting the concentration profile, what we do, we try to look at the energy equation and its simplification as well as per the constraints of the problem. Energy equation we have derived in equation, we have derived in week number 4. So, this is what we have got, whereas this E is there in all 3 direction, x, y and z direction, and then each E, and it consists of a contribution from the conduction, convection, work done because of the pressure, viscous dissipation, etc. all those terms are included in all 3 directions, right. So, whatever the energy because of the gravity is there, so then that part is in the last, it is given, right. That's potential energy, etc. those things are coming from here. So, this equation we know. Okay. So, if you expand this equation, only this part we are expanding, because this E is having all the components, like all the contributions from the conduction, convection, viscous dissipation, work done because of the pressure, etc. all those things, right. Then we simplify it. So, this if you expand, you get dou Ex by dou x plus dou Ey by dou y plus dou Ez by dou z. So, that is written here. So, now we apply the constraints of the problem, steady state. So, then left hand side all terms are cancelled out. Gravity we are taking in the other direction. So, in the direction of diffusion or temperature variations whatever are occurring, in that direction there is no gravity. So, this we can take out 0, right. So, the variations in the energy or temperature are occurring only in the y direction, and that is function of y. So, remaining Ex, Ez are 0. So, what we get, dou by dou y of Ey is equals to 0. This is what we get. Now, to determine the mole fraction profile, we need the molar flux for diffusion of A through stagnant B. So, this how do we get? In general, we write a combined flux equation. So, that is this one. Now, in this equation, NBY is 0 for part A of the problem. So, if you simplify this equation by taking all NaY terms one side and then remaining terms other side, you get NaY is equals to minus C dAB by 1 minus XA dou XA by dou y. So, now this you can substitute in dou NaY by dou y is equals to 0 and then get the concentration profile as function of y. So, when you substitute, this is nothing but NaY term, we substituted d by dy of NaY is equals to 0. So, NaY is this one. Now, for this situation, part A situation, the concentration and then diffusivity we can take constant. Then we have a integral of d by dy of 1 by 1 minus xa dxa by dy is equals to 0 dy, that is 1 by 1 minus xa dxa by dy is equals to C1. Then further integrating, you get minus ln 1 minus xa is equals to C1y plus C2. Now, we have two boundary condition at y is equals to 0, xa is equals to xa naught. So, here if you substitute xa naught, you get minus ln 1 minus xa naught is equals to C2, because y is 0 in this boundary condition. So, C2 you already got. Then other boundary condition at y is equals to delta, xa is equals to xa delta. So in place of XA you write XA delta, in place of Y you write delta, and then C2 you already got it as minus ln 1 minus XA naught. Then you get C1, that is nothing but 1 by delta ln 1 minus XA naught by 1 minus XA delta. So this C1 and then this C2 we are substituting in this equation to get the concentration profile. This term is C1 and then this term is C2, right. Then if you further simplify in the sense what we do, we take this minus ln 1 minus XA naught to the left hand side, so that we can write ln 1 minus XA naught by 1 minus XA is equals to Y by delta ln 1 minus XA naught by 1 minus XA delta. So this is the final concentration profile. Further you can write by taking this Y by delta as a power of the whatever ln of 1 minus XA delta by 1 minus XA naught, then you have this one. If you take exponential both sides, you get this as a concentration profile, right. Of course, any of these two equations you can use as a concentration profile, right. Now what we do, we differentiate this equation with respect to Y, because we wanted to know the flux also. We have to find out the mass flux also. For that we need to know dxa by dy. So that is the reason we are differentiating this equation with respect to Y. So this from this term what we have, 1 by 1 minus xa minus dxa by dy. This is constant, so 0, derivative of constant is 0. Now this equation except Y everything is constant, so 1 by delta ln 1 minus XA delta by 1 minus XA naught multiplied by 1, right. So now flux of component A, what we have, minus C dAB by 1 minus XA dXA by dy, this is what we derived. So that means this equation if you multiply it by C dAB, you will get flux, that is given by this equation, right. Now what we got a expression for the concentration profile, we got a expression for the flux also. So then what we try to do, we try to write these expressions, concentration profile in a very conventional way of writing, like what in general what we write, XA minus XA delta divided by XA naught minus XA delta, in this form we try to write. So that is what we are doing in the next slide. So NAY is equals to this one we have. So from this equation I can write NAY delta C dAB one side and then ln terms other side. Then I am taking exponential here. Then I am multiplying by minus 1 either side and then adding plus 1 either side. Then in the left hand side what I am doing, I am trying to do LCM, so that I have XA delta minus XA naught divided by 1 minus XA naught is equals to right hand side term as it is, right. If you wanted to know XA minus XA naught divided by 1 minus XA naught expression, so then what you have to do, simply you have to replace this XA delta by XA, and then here whatever delta is there, that you have to replace by Y, because at Y is equals to delta, XA is equals to XA delta. At Y is equals to some unknown Y, XA is equals to some unknown XA, right. So that if you do, you get this expression. Now if you divide this equation by the above equation, then you get XA minus XA naught divided by XA delta minus XA naught is equals to 1 minus exponential of NAY Y divided by C dAB divided by 1 minus exponential of NAY delta divided by C dAB. This is what we have, right. Now we try to get the temperature profile. So what we got by simplifying the energy equation, we got dou by dou Y of EY is equals to 0. But what is that EY, we have not simplified in that slide, so that we are doing here. So the E is having the contribution from the conduction, convection, then any work done because of the pressure, and then any molecular stress, energy because of the molecular stresses like viscous dissipation, etc. Those terms are including. But now we have to incorporate a term because of the mass transfer also. remember when we are deriving the energy equation, we had incorporated most of the common contributions which are important from chemical engineering applications, specific to the mass transport problem or heat transfer problem, like that, specific to the heat transfer problem only. But at the same time, what we have mentioned, if any additional contributions are coming because of the reaction or mass transfer, etc., so those terms should be added up in this expression or final energy equation that we have derived. So either way we have to do, that is what we have discussed, because in a generalized manner we cannot include each and every terminology like nuclear power, energy associated with the electrochemical reactions, energy associated because of the hydrodynamic, magnetohydrodynamics, etc. All those things we cannot include because they are specific to the problem. So now specific to this problem, we have to incorporate a term related to the mass transfer, how it is affecting this E or the heat transfer problem. So if you can understand clearly, you can simply add sigma n alpha Cp bar delta T, that you can do it, right. So but if you are not able to understand how it is coming, so then we have to do this one. So before adding we will be adding that mass transfer part here, but also we are doing some kind of readjustment in the sense this conduction term we are bringing here, right, and then this whatever the mass transfer, because of the mass transfer the contribution should come in E, that is nothing but sigma H alpha bar J alpha. J alpha is nothing but molar flux because of the diffusion, and then H alpha bar is nothing but the enthalpy of component, molar enthalpy of that component alpha. There are n number of components, right. So now in the next step, from this PV and then this rho V, we are combining such a way that rho U tilde plus P V tilde V, and then remaining of rho V square V we are writing here. Tau dot V is as it is. In place of minus whatever the minus K delta T is there, that we are writing first, and then this flux terms we are writing as a second one. Why are we writing? So that this U plus PV we can write H. So now here H tilde, we are using tildes. So we are writing for only one component. So there are n number of components should be there. So then we have to write a summation. Remaining two terms are as it is. Okay. Now next step, what we are doing, this term we are multiplying by the molecular weight of that component alpha and then dividing by the same. Why are we doing? Because we can write this rho alpha by m alpha, we can write C alpha, and then that C alpha V we can have a relation for in terms of the flux. So that is the reason. So C alpha H alpha bar V we are having here. But we know that n alpha is equals to C alpha V alpha, and J alpha is equals to C alpha multiplied by V alpha minus V. This we have already seen in the beginning, in the first lecture of mass transfer part, right. Now this J alpha, if I expand, C alpha V alpha minus C alpha V. So in place of C alpha V alpha I can write n alpha. Now from here I can write C alpha V is nothing but n alpha minus J alpha. So this we are going to use in equation number 4. Here what we had, C alpha V. So in place of C alpha V we are writing n alpha minus J alpha. So that this H alpha bar J alpha and then this H alpha bar J alpha cancelled out, and then we have only sigma H alpha bar n alpha, right. Now this, if you write for the binary component, you have H alpha bar, you have HA bar NAY plus HB bar NBY, and then conduction is also only in the y direction, so minus K dou T by dou y. Now this HA bar and then HB bar we can replace by CPA bar delta T, but NBY is anyway 0 in this problem, so that NBY CPB bar delta T we don't need to write. So now this equation you can substitute in dou by dou y of EY is equals to 0 and then simplify to get the required temperature profile. So, dou by dou y of Ey is this one is equals to 0. This we integrated one, so this term as it is equals to C3. Now, next step we are keeping minus k dou t by dou y one side, all other terms we are taking other side. Next step what we are trying to do, we are writing dt by dy is equals to NAY CPA bar by k t minus t naught minus C3 by k. So, next step dy term we are keeping one side, all other term we are taking the other side. So, dt by this term you will be having, right. Now, what we can do, you can integrate. So, when you integrate you get ln of this term divided by the differentiation of t terms. So, then that is Na CPA bar by k you will get as a denominator, right side you get y and then constant C4, right. So, now we have two boundary conditions, two constants we can evaluate. So, at y is equals to 0, t is equals to t naught. So, then here when you substitute t by t naught, so then you get this term is 0, then that means what you get, C4 is nothing but ln of minus C3 by k divided by Na CPA bar by k. Now, we apply the other boundary conditions, y is equals to delta, at y is equals to delta, t is equals to t delta. So, then here t delta we are having, in place of y we are having delta, right. So, now what we do, we take this term to the right hand side, so that in the right hand side we have this one, right. Next step what we are trying to do, we are writing exponential rather writing in ln terms. So, then this is what we have. Next step what we are trying to do, we are taking this C3 by k to the right hand side, right. Next step what we are writing, in place of C3 by k we will be writing minus exponential of NAY CPA bar by k C4, which we just derived in the previous slide by applying the first boundary condition. This is what we got. So, that you substitute here as this term, remaining all terms are same, right. So, that the same equation is written once again here. So, now what we do, we need to have t minus t naught also. So, that in place of t delta we write t, and in place of delta we write y, right, because at y is equals to delta, t is equals to t delta, and then at y is equals to some unknown y, t is equals to some unknown t, right. So, that if you do, you get this equation. So, now you do 12b divided by 12a equations, then you get t minus t naught divided by t delta minus t naught is equals to this one. Next step what we do, we take this term common from both numerator and denominator, so that that can be cancelled out, and then we have this particular term. Now, this is exponential of a by exponential of b form. So, we can write exponential of a minus b. So, that you write. So, then this would be cancelled out. So, in the exponential we will be having only one term, both in numerator and denominator terms. That we can write now, t minus t naught divided by t delta minus t naught is equals to 1 minus exponential of NAY CPA bar by k y divided by 1 minus exponential of NAY CPA bar by k delta. So, this is the temperature profile, right. Now, we try to find out the rate of heat transfer as well, right. So, before going into the finding out the rate of heat transfer, what we understand from here, until and unless NAY CPA bar by k is tending to 0, this temperature profile is not linear, it is non-linear. Okay. It can be linear only when this particular term tends to 0, right. That is, what does it mean by, when the conduction is very much dominating compared to the mass transfer, then only we can have a linear profile. Obviously, if there is only conduction, so then temperature profile is linear, that we know. Okay. Now differentiating with respect to y, so in the left hand side 1 by T delta minus T naught is constant, then dt by dy minus 0 is equals to, and then in the right hand side except this particular term, all other terms are independent of y. So in the denominator we are keeping as it is, numerator when you are differentiating this term, exponential of x is exponential of x on differentiation. So you get the same thing minus exponential of same term, and then differentiation of whatever these factors being multiplied by y. So that is NAY CPA bar by k, right. So now we wanted to know minus k dou t by dou y. So minus k dou t by dou y. So then what we are doing, this T delta minus T naught we brought to the right hand side, okay. And then this whatever this 1 by k was there, so that we have taken to the left hand side. So then we have k here. So now this we wanted to do at the cold surface, because at that point how much heat transfer is taking place, because that is the location at which condensation is taking place, right. So in this equation if you substitute y is equals to 0, so the exponential of something multiplied by 0 is 0, so exponential of 0 we take 1. So remaining terms are anyway constant, so they remain as it is. Now this is the rate of heat transfer when there is a mass transfer. NAY is there, that means NAY associated with the mass transfer. So mass transfer contribution has also brought into the temperature profile and then subsequent heat transfer. But if there is no mass transfer, then in the absence of mass transfer, temperature profile is linear, that is this one. How do you get? So if there is no mass transfer, dou by dou y of Ey is equals to 0, and then Ey would be having only minus k dou t by dou y term only we will be having, right. So that means dou square t by dou y square is equals to 0. So t is equals to C1y plus C2 you get, you apply y is equals to 0, t is equals to t naught, y is equals to delta, t is equals to t delta you apply, and then obtain this constant C1, C2 and then simplify. So then you get t minus t naught by t delta minus t naught is equals to y by delta. So that we have written directly, right. So now in the absence of mass transfer we have this linear temperature profile. For this case also we try to find out the rate of heat transfer. So for that we get dt by dy, which is nothing but t delta minus t naught by delta. And now we are multiplying by minus k either side and then substituting y is equals to 0, and then this superscript naught is indicating in the absence of mass transfer, so that we can compare the rate of heat transfers in the absence and then in the presence of mass transfer. So that we do, this is in the presence of mass transfer, how the rate of heat transfer is being affected. So that is one, this is in the absence of mass transfer. So then this quantity will give the relative contribution of mass transfer on the relative heat transfer rates by including the mass transfer and by without including the mass transfer, right. So what we understand here, the heat transfer part is clearly affected by the mass transfer or mass flux, but the mass transfer part there is no heat transfer effect. Why that is? Because whatever the D, C etc. are there, how are they related to temperature, that is not given. So that is the reason we did not bring this term effect of temperature in mass transfer, okay. Now we take part B. Part B is what? Both A and B are diffusing, A and B are condensing. So there is nothing like non-condensable thing here, and then this delta x is not equals to delta t is not equals to delta. We have to generalize. But first what we do, we take only this thing, and then we take delta x is equals to delta t is equals to delta 1, same constant, film thickness is same whether mass transport or heat transport, right. However, unequal film thickness we later on incorporate, Okay. So, when both components are condensing at wall, so pictorially the same thing is shown here, right. Same horizontal axis is y axis, and then condensable vapors are coming in this direction, and then they are reaching the cold surface, and upon reaching the cold surface they are condensing on the cold surface. At cold surface, that is at y is equals to 0, T is T naught, Xa is Xa naught, and then at y is equals to delta, T is T delta, Xa is Xa delta, because the film thickness is delta. Now, both A and B are coming and condensing on the vapors. So, we cannot say that NBY is 0 here in this case. So, mass balance for component A, if you wanted to do, but by taking a film in between of thickness delta y. So, whatever the flux Na y at y is equals to y is entering flux, and then whatever the flux that is leaving at y plus delta y is NaY at y plus delta y, and then both of them are multiplied by the cross section area of the surface through which the channel of thickness delta y, that is S, we have taken. So, we can do balance this way, or in the part way we have directly taken the species conservation equation, dou Ca by dou T plus del dot Na is equals to 0, that we have taken. So, that way also we can do it. Okay. So, now you apply limiting conditions after dividing this equation by S and delta y, then you get this equation. Now, this is NaY is equals to constant. So, what is that constant? We do not know. So, we are calling it Na naught, right. Similarly, if you do for component B, you get NBY is equals to constant, and that constant we do not know. So, we are calling it NB naught. So, now energy equation, simplification of energy equation is exactly the same as we have done previously, right. So, but that dou by dou y of Ey is equals to 0, and then Ey is equals to E naught. That constant we do not know, we are calling it E naught. Now, the combined flux equation is given here. So, now here in place of NaY you have to write Na naught, and then in place of NBY you have to write NB naught, right. So, when you write, you get this equation. Now, here E up to this point we have simplified in the part A, right. So, it is same here also, exactly same, right. Now, what we do, this one we write for the binary component, then we have minus k dou T by dou y plus H A bar NaY plus HB bar NBY, right. In the previous case we have taken NBY is 0, and then H A bar we replaced by CPA bar delta T, but now we cannot do that one. This NaY is Na naught, and this NBY is nothing but NB naught, and then HA bar is CPA bar delta T, HB bar is CPB bar delta T. So, that when you do, you get final E expression, this one, right. So, that is minus k dou T by dou y plus Na naught CPA bar plus NB naught CPB bar multiplied by delta T is equals to E naught. That E naught we are evaluating at T is equals to T naught. So, then at that point we have only conductive heat flux at the wall, there is no mass transfer. So, that we calling Q naught. Okay. Now, in equation 4, this is the equation 4 that we had. So, we are adding minus Na naught plus NB naught Xa naught both sides. So, there is a reason we are neither solving this equation number 4 or equation number 7 directly, right. What we are trying to do, we are adding this term to the equation number 4 both sides. So, then we have this component in the left hand side, and then in the right hand side Na naught is already there. So, minus Xa naught Na naught plus NB naught, right. So, the reason is that now this equation number 8 and then equation number 7, if you compare, they are exactly similar, right. only thing that K is replaced by CDAB and then T is replaced by XA. Then NA naught is replaced, NA naught CPA bar is replaced by NA naught and then NB naught CP bar is replaced by NB naught, T is replaced by XA and then T naught is replaced by XA naught and then Q naught is replaced by this particular term in the right side of equation number 8. So that they are quite similar to each other. So you can solve one equation, you can solve any of this one equation and then analogously you can write the solution for the other equation. Right. So what we do now, we solve this equation number 8. So for that this particular term we take to the right hand side, but we do not simplify. So then we have this thing and then left hand side we have only minus C dAB dXA by dy. So the same is written once again here. So now here y dy by C dAB we are taking other side and the rest other terms dXA by all these NE naught, NB naught terms we are keeping in the left hand side and integrating. So the integration constant C1 is there. Right. So this one is minus ln of whatever this term divided by differentiation of the XA terms. So that is minus NA naught plus NB naught. In the right hand side simply y by C dAB we are having plus this constant. Right. So now we apply boundary condition y is equals to 0. So XA should be XA naught. So that if you substitute XA is equals to XA naught here, so the second term would be 0 within the logarithmic and then right hand side this y is 0, so this term is 0. So directly you get C1 as this one. Now this C1 we are going to substitute here and then simplify. So that C1 we have substituted here. Now this minus you can cancel out and then this NA naught plus NB naught you take it to the right hand side and multiply by these two terms. Then what you have, left hand side this term, in the right hand side NA naught plus NB naught y C dAB should be there and then second term NA naught plus NB naught is cancelled out, only ln NA naught minus XA naught NA naught plus NB naught would be there. So that we brought to the left hand side, directly I have written. So now this is ln A minus ln B form. So I can write ln A by B, so that I write and then simplify, I get 1 minus NA naught plus NB naught XA minus XA naught divided by NA naught minus XA naught. NA naught plus NB naught is equals to NA naught plus NB naught y by C dAB. Right. So after removing this ln in terms of exponential issue, right. So this is the expression for the concentration profile XA as function of y for the second case. Right. So now this is for this equation number 8, equation number 9 is the solution. Right. Now our equation number 7 is similar as equation number 8. So its solution should be similar to the equation number 9. So that you have here, NA naught has to be replaced by NA naught CPA bar and NB naught has to be replaced by NB naught CPB bar and delta x should be replaced by delta t, and whatever NA naught minus XA naught, NA naught plus NB naught is there, that should be replaced by Q naught. Right side also the same thing we are doing, and then C dAB should be replaced by K. Right. Now what we do, the limiting conditions of unequal film thickness. If the film thickness are unequal, then at y is equals to delta x, XA is equals to XA delta. This is for the mass transfer part, right. So film thickness for the mass transport whatever is there, delta x. So under such conditions XA is XA delta, and then for the heat transfer part film thickness is delta t. So then y is equals to delta t, t is equals to t delta t. up to getting the solution of equation number 8 in the form equation number 9, what we have taken? We have taken delta x is equals to delta t is equals to delta, right. But in the problem we have unequal film thickness, so then accordingly we have two different boundary conditions, right. So now in equation number 9, wherever xa is there you replace by xa delta, and wherever delta is there, wherever y is there you replace by delta x. Similarly in equation number 10, which is the heat transfer solution, so you replace t by t delta and then y by delta t. Then you have this equation number 11 and 12 as solutions. So now this is concentration profile when film thickness is delta x for mass transfer, and then this is the temperature profile when film thickness is delta T for heat transfer, right. So the references for this lecture are provided here. Thank you.